All right, continuing on to a part 2 for today's lecture. Just wanted to break the video up there a little bit so I could have a separate file for just that example problem. Now I want to move on to a discussion of kinetic energy, working with the conservation of kinetic energy of a system of particles. So kinetic energy. Let me make sure something here. Kinetic energy, we're good, okay. Kinetic energy of a system of particles. Kinetic energy of a system of particles. So, let's see. Well, let me draw out a system first. Okay, so let's say we have this. Here, well, first I'll have a global coordinate system. Actually, I'll put it over a little more, just give myself a little more room. So let's say I have X, Y, and Z. And then at the origin. And then I have point G, which again, what is G? What is G? G is the center of mass, or the mass center of our system of particles. So G is going to be the mass center of our system of particles. So if I'm defining a new coordinate system about the mass center, G here, and so I would have a x prime, a y prime, and a z prime. And then I would have some velocity v here, v bar, for instance. That would mean v average. So the a v bar here, or just a v, vg or something like that. But anyway, the v of the center of mass would basically be the average velocity of the system of particles. And then I could also have some particular pi, some particular particle, pi, an arbitrary particle pi, something in a particle swarm or a group of particles or a small collection of particles, something like that. And this would have a, you would have a global vi, but this would have two components essentially. It would have component v average and just a component vi prime. So let me annotate this a bit. A particular particle has a velocity, a global velocity in the global coordinate system vi. In the coordinate system, centered at the mass center, it has a velocity vi prime. Has velocity vi prime. And the relationship between these, one way you can look at it is a component relationship like this. So you'd have something, if I were to expand this a bit, I could have basically vi and also the average. We could look at it a component way. We could look at it as a vector sum as well, and vi prime. So something like a component, or more accurately, probably a vector sum interpretation. But regardless, the overall relationship here would be that VI is equal to VG equals VI prime. Or VG is the same thing as V bar. Oh, sorry, VG plus VI prime. Or V bar plus VI prime. Okay. So then we can, from this, I can look at the, since I have this VI here, I can look at the kinetic energy of the system. And the kinetic energy of the system now, have you ever sat back and thought about this? Like, is kinetic energy constant across reference frames? Is it? That's just a question. Is kinetic energy constant across reference frames? If you were to perform a measurement of different things, different objects, and ask people standing in different places how much kinetic energy that thing would have, you could actually get very different answers. So, for example, if you were standing on a train and the train is going by at 50 miles, is going down the tracks at 50 miles an hour, or in a plane even or something, and say you're in a plane, the classic expression of this is always trains, but I guess more modern, maybe planes. A plane going 500 miles an hour, and you are sitting in the plane, and you ask the person next to you, how much kinetic energy do I have? Well, for when they measure your velocity, they will say you have no velocity. So they will say your kinetic energy, aside from minor things of you moving your body about and things like that, they'll say your kinetic energy is zero. But someone sitting on the ground will say, oh my goodness, you have a tremendous amount of kinetic energy. You're traveling 500 miles an hour. They'll take your, let's say 1/2 mv squared, throw in 500 miles per hour in there, and get that you have a very large kinetic energy. So kinetic energy actually depends on the system of reference. If you are in it depends on the reference frame that you're looking at. But anyway, in our global reference frame here, T is equal to 1/2 times the summation of basically all of our mv squareds. So mi times vi dot vi squared. So I'm trying to express this in vector notation. We're used to seeing kinetic energy is 1/2 mv squared, but if we want to use it in more of a vector form, I would say that it's the dot product of itself squared. It's the dot product of itself. Actually, not squared, just the dot product of itself. And that will produce a single number. See, the thing about kinetic energy is energy a scalar or a vector? Energy is a scalar, yes. Things like momentum, angular momentum, linear momentum, velocity, acceleration, displacement, those are vector quantities. They have both a magnitude and a direction. Something like kinetic energy, though, it only has a magnitude. There is no such thing as saying, oh, it doesn't make any sense to say, I have a kinetic energy of 10 joules at an angle of 20 degrees. That doesn't make sense. I don't say I have 20 joules of kinetic energy upward. I mean, I can have a velocity of 20 that will produce I can have an upward velocity that produces a kinetic energy of that much, but the velocity itself, the kinetic energy itself does not have any kind of direction to it. It is a purely scalar quantity. So vi dot vi, which is then equal to 1/2 times the summation from 1 to n, from I equals 1 to n of mi, or simply mi vi squared, if I'm looking at just the components, just the magnitudes, rather than the, see, if this would be the magnitude of vi rather than the vector form of it. Okay, so what if I want to transform this and instead look at the centroidal reference frame, the reference frame centered at G? So now express kinetic energy in a centroidal reference frame. in a centroidal reference frame. So T equals 1/2 times the summation of I equals 1 to n of mi times Vg plus Vi prime, both of these vectors, dotted in to Vg plus Vi prime. How in the world did I get this? Where did this come from? Where this came from is I took the equation here, this equation here, and replaced Vi vector with Vg plus Vi prime. Oh, and these should actually have a vector sign on them. Sorry about that. That should have a vector sign on it. And same with this and this. Okay, so all I did was I just replaced the global Vi with the summation of the velocity of the centroid itself plus the velocity of the particle relative to the centroid. And we'll get there. Why I'm doing this, we'll get there. You'll see. We'll eventually reach something at least a little bit useful, partially useful. Yes, thank you. There should be a bracket on the end. Yes, thank you. Okay, so this is then equal to 1/2 times, if I just sort of start separating out some quantities, the summation from I equals 1 to n, I equals 1 to n of mi times Vg squared plus Vg dotted in to summation of I equals 1 to n, I equals 1 to n, I equals 1 to n, if I can manage to keep from mangling my own words, mi Vi vector prime plus 1/2. So this is a term here, here. And then, actually, let me think about that. Vg dotted into the summation of that. Yeah. Plus this is 1/2 times the summation of I equals 1 to n of mi Vi prime squared. And finally, this will reduce then down to 1/2 m Vg squared. So now we're actually getting something useful. This is sort of the final application of this, or the final form. 1/2 mVg squared plus 1/2 times the summation I equals 1 to n of mi Vi prime squared, non-vector, scalar only. And what is important to this is that, and this makes sense, kinetic energy is equal to the kinetic energy of the center, the mass center, plus kinetic energy relative to centroidal frame. If I can write plus correctly. Plus Ke of plus Ke relative to centroidal frame. Plus Ke of centroidal frame. So maybe I can work through a very simple, brief example on this. Again, it's just going to be based off of transforming from local to global, global to local, all of that kind of thing. And I just want to illustrate a very simple example. You know what, maybe I'll actually work through an example with some numbers on with our plane example. So let's find out. Let's explore this a little bit. Okay, So let's say there is somebody, and I'm not very good at drawing airplanes. I'm not really good at drawing much, as you all know by now. So, example, let's say we have a plane. And this is my wonderfully rendered plane. And this plane is going, let's see, let's say 200, 500. I'm just doing a little conversion here. I'm just going to do this in metric for simplicity. Let's say it's going 225 meters per second. Meters per second, east. Okay, 225 meters per second east. And there is somebody standing in this plane. And then another plane nice rectangular plane, as everyone seems to make. And you've all seen those rectangular planes in the sky, right? And they're not very fast or efficient, but they sure are cheap to build. Maybe. And then we have another crudely drawn plane. And this is moving, 300 meters per second west. And there's another person standing here. This is not to scale. Otherwise his head would be sticking out of the plane. I don't recommend sticking your head out the plane window and it's going over 500 miles an hour. You're going to have a bad time. Please don't do that. In fact, actually, I should probably draw the head just like... Actually, yeah, let me just... There we go. Yeah, the head just kind of went flying away. But, well, no, I need the head there because I need to be able to measure something. And oh, I just erased the plane. What am I doing here? Okay, another person here. Okay, so I have this, and I want to find out, or what I want to find out is this. Let's call this plane A and plane B. What will the person in plane B measure A's kinetic energy as? Kinetic energy as, assuming plane A, or assuming person A has a mass of 40 kilograms. Has a mass of 40 kilograms.
What will the person be measuring? So you're measuring plane A's kinetic energy, or the person's?
The person's. What will the person? Yeah. Let me like clear that that we're talking about the person's. Person A's. What did I do? Pen. Measure persons. A's kinetic energy. And you know what? Let's just for fun say this person is maybe on a dirt bike or something going really fast down the aisle of the plane, and they're going 20 meters per second that way or something. Okay? Let's say person A is going backwards in the plane. Let's see if we can get this to work without...
Sprinting to the back?
Yeah, at 20 meters per second. That would be pretty impressive. I wouldn't even be mad. I'd just be impressed. Okay. So, let's look at this. Well, we're going to say, well, the solution here, it's going to be fairly straightforward. We will measure the T, the kinetic energy, as 1/2 mvg squared plus 1/2 summation of mi/vi squared, or vi prime squared. Now, our for person A, the the VI prime is basically going to be the reference frame of the airplane. So I would say that it would be, in this case, 1/2 times 40 kilograms. That's not going to change. Times the velocity of g. This is going to be the overall velocity of the plane A relative to B, because I'm just considering the entire plane A to be the reference frame that this guy is moving in. And so I'm going to say positive 525 meters per second. Because we have to base this off of relative velocities. And I'm basing this off the relative velocity between the two planes. Squared. So this one's actually going to utterly dominate everything, in case you couldn't tell. 1/2, or actually, I guess we could make that 50 meters per second. Maybe if they're throwing a baseball or something, or maybe there's like a catapult inside the plane. The person is an electric catapult, a rocket catapult or something inside the plane. That, anyway, let's just say this person is somehow running at 50 meters per second inside the plane. Don't do that inside an airline. The TSA will be mad. 40 kilograms times 50 meters per second. It's still going to dwarf it, but less so. So let's work through some of these numbers. Anyone? I'll actually put in the negative here just to make clear that the negatives will cancel out. So that's then going to be 0.5 times 40 times 525 squared, which is 5.5 times 10 to the 6th, either the 6th, or 5.51 maybe, if I want to leave a little more sig figs. 5.51 plus 0.5 times 40 times 50 squared, and that's just 50,000. So yeah, this is just utterly dominating it. I probably should have chose a system with more compatible velocities, but oh well. The idea is the same. And I get, finally, well, we'll change it slightly. We will get 5.56 times 10 to the 6th joules. 5.56 times 10 to the 6th joules will be our final measured kinetic energy of person A or object A, depending on what we're launching via, et cetera, et cetera. And that's the basic idea.
Does it matter that they're moving negative direction?
Now, interestingly, the question was, does it matter that they're moving negative? And I included that negative here. I included the negative here. Although, we have to be very careful with this. That I think about this, this might not be, this is how you'd handle one problem, though. Then I'm thinking about this might not actually be appropriate. I think I may have flubbed this up a little bit, because, does anyone see the problem with this?
You're adding their energy, but I just feel like they're moving that way really fast, but they should be taking away something.
Here's the problem. The problem is that now that I'm looking at this is actually maybe not quite proper, because these equations are built for a swarm of particles. And so, in order to do this properly, I'd have to consider the mass of I would have to consider the plane itself to be another one of the particles. And I would take the 225 as the velocity of the entire thing, the average velocity, and the average velocity would actually be decreased because one part of it is moving, one tiny bit of the mass is moving to the left. So this is not necessarily exactly appropriate. In reality, I would have to add one more term, including the, I would have to decrease the combined velocity slightly, because it would be moving, I would have to find the centroid of this whole system, and it would get a little messy. But do you kind of see how you would do that? But this is just kind of the illustration of how you would, well, that's the danger of coming up with problems on the fly. But that's the basic idea. We're going to break it up into two pieces, multiple pieces. In this case, I would want to also look at the plane as another one of my summation objects, et cetera, et cetera. Okay, anyway, let's move on to the work energy principle. So that example is a little flawed. Let's just put this a little flawed, and then I think about that. A little flawed. Need to treat plane and person as distinct objects. We can probably do better. Plane and person as distinct objects. Something like that. Okay, and we will see some more of that as we go along. We'll see some better examples. Okay, so let's now look at the work energy principle and conservation of energy for systems of particles. The work energy principle for systems of particles. Okay. So, well, the principle of work and energy can be applied to each particle P. Applied to each particle Pi. To each particle Pi. And the basic idea, T1 plus U from 1 to 2 is equal to T2. So the initial kinetic energy, so again, we're using T for kinetic energy. So the initial kinetic energy, the kinetic energy at point 1, plus any work done on the particle from point 1 to 2 will produce final kinetic energy T2, where U1 to 2 represents the work done by the internal forces, and external forces. Work done on internal forces Fij and the resultant external forces force Fi acting on Pi. Acting on Pi. Okay? So the principle of work and energy and energy can be applied to the entire system. So we've seen that, as I mentioned, it can be applied to one particle, and energy can also be applied to the entire system. Be applied to entire system. To entire system. By adding Ke, by adding the kinetic energy. Kinetic energies of all particles. Kinetic energies of all particles and considering the work of all internal and external forces. And external forces. Of all internal and external forces. And so, okay. So again, we can look at things as either individual particles. We can look at the, the work and energy applied to a single particle, or we can look at it applied to the entire system of particles. Now, what's going to be different about this one is we could do that with momentum. We were able to do that with conservation of momentum yesterday. What's going to be different between this and energy is the internal forces. The internal forces, things like internal electric charge, gravity, what have you, that's what's going to be different. See, what I mean by this is the internal forces will be different, or the action of, or the effects of. Internal forces will be different. Will be different than external forces. Sorry, than in the previous case of momentum conservation. In the previous case of momentum conservation, and the reason is simple. Momentum conservation and momentum, because of the basic, okay, actually, let me go back here. Internal forces are always equal and opposite within the system. Are always equal and opposite. Thus, for momentum, they're just going to cancel out. For momentum, they will cancel out. Meanwhile, for momentum, they're just going to cancel out. But for kinetic energy, we look at kinetic energy, 1/2 mv squared. For kinetic energy, will not cancel out. They generally will not cancel out. So even though the forces that are, remember our Fij, Fji, even though these are equal and opposite, they will not cancel out. The work produced by them will not cancel out because we're looking at kinetic energy is the velocity squared. However, if forces acting on the particles are conservative, acting on are conservative, here, we can have another relationship. Are conservative, the work is equal to the change in potential energy. To the change in potential energy. In potential energy. Where essentially K1 T1 plus V1 equals T2 plus V2, where T is our kinetic energy and V is our potential energy. So again, this is conservation of energy for a system of particles. For a particle system. For a particle system. Okay, questions on that? Okay, how are we doing time-wise? I think that's a little more time before we take a break. Actually, let me look a bit further on some things I might want to look at. Gaining and losing mass, dreams. Okay. I think we might take a short break there. I think that will do it. We'll come back and look at some further new material.